now that we have talked about the electrophilic addition reactions of HX to alkenes and the corresponding or the associated Markovnikov rule, I would like to take a detour to talk about the so-called Wagner-Meerwein rearrangement, or also called Hydride shift. And this effect is described on this slide here. So we are starting with the starting molecule 3-methyl-but-1-ene, and we are having a terminal double bond. So we are getting on the addition of a proton here, stemming from our HX, we are getting, as we just discussed with the Markovnikov rule, we are getting this secondary carbocation. And now you might think, okay, everything is fine. I've understood the Markovnikov rule. So I expect that this is clear to me. This is the more stable carbocation because it's a secondary composed to the primary carbocation that would be the alternative in this case. So our X just adds to this secondary carbocation, and we get, as we would expect, the secondary halogen alkane. But to our surprise, this is actually just the minor product. What happens here is shown here in this part of the slide on the right side, and we are observing a so-called 1,2 hydride shift. So what we see here is that the sigma bond, the carbon sigma bond with the between the carbon and the hydrogen, is completely transferring towards this secondary carbocation. And what is the driving force here? That's the formation of a tertiary carbocation, because we're moving from a secondary carbocation that we started with to a tertiary one. And this one is again more stabilized than the secondary one. So this one here is favored. And then, only then, our X minus, our nucleophile, adds to our intermediary carbocation, and so we are actually getting a tertiary halogen alkane as our major product. And this, of course, if you see this initially, this is quite surprising because the H, the hydrogen, and the X, the halogen that we add here, are not directly added to the former double bond, but are actually added in 1,3 position in this case. And this is quite surprising, but it's actually not that surprising when you understand that this molecule, or this carbocation, stabilizes even more by this so-called 1,2 hydride shift. And the same also happens when you start out with 3,3-dimethyl-but-1-ene. And here in this case, we are not having a hydrogen atom in that shifts, but we rather have a methyl group that shifts. So this is not limited to hydride atoms or hydrogen atoms, but also methyl groups can shift around. And so here again, driving force is again the same as with the hydride atom or the hydride shift. The secondary carbocation gets transformed into the tertiary carbocation. This is more stable, so this tertiary halogen alkane is the major product here. So to summarize for the Wagner-Meerwein rearrangement, always be on the lookout if you can maybe form a more stable carbocation by the shift of a methyl group or a hydrogen atom at this intermediary carbocation.